Good morning, dear students. Today we are going to start our first unit in class 9 mathematics, that is called number systems. So in this number system, we will be discussing natural numbers, whole numbers, integers, then rational numbers, irrational numbers, and subsequent discussions. So let me start with the rational number first. Natural number first. You know, Let me share the screen with you first. So dear students, as you see, the natural numbers or the numbers, the collection of natural numbers is denoted by capital N and is written as capital N equal to 1, 2, 3. Here I wrote one number 135 and so on. It actually goes to infinite. You know, we define this set of natural number in a set notation form. As you see, it is within the bracket, and it is an uncountable set. That means there is you cannot say how many natural numbers exist. Okay, so there is no last natural number. That's why I said, okay, there is no last natural number, and we define this natural number is by capital N. In simple terms, we can say the natural numbers starts with 1 and it is actually incremented by 1 and goes on. So as you see here, I wrote, 1, 2, 3. In that way, it goes, you'll get one number called 135 and so on. Okay, so this is called the natural numbers. The next number system, what comes after natural number, is called the whole number. A collection of whole numbers is denoted by W, and let me show you how it actually being described. As you see, the collection of whole numbers is denoted by capital W and is written as capital W equal to 0, 1, 2, 3, and it goes on. In other words, we can say that the whole numbers W is nothing but 0 and all the natural numbers. So in set theoretic notation, dear students, we can write W is equal to set 0 and then union of the set of natural numbers. Okay. The collection of whole numbers is 0 and the collection of natural numbers, that is we defined as a whole numbers. I hope it is clear. And after that, it comes with an integers. What is an integer? So let's define this thing first. As you see, dear students, the collection of integers is denoted by Z and is written as, it starts from minus infinite, okay, and goes to plus infinite in such a manner. The middle number is 0, okay, and it incremented by 1. You see, from 0 we go in the right hand side 1, 2, 3. In that way, it goes up to infinite, okay, and in the left hand side also -1, -2, -3. In that way, it goes up to minus infinite. So the collection of integers is denoted by Z and is written as like this, as you see. So what we can say is that, from a set theoretic notation, set of natural numbers is a subset of set of whole numbers, is a subset of set of integers. Or the other way we can say, the set of integers is a superset of set of whole numbers, is a superset of set of natural numbers. Correct? I hope it is absolutely clear about the integers. Our next point of discussion is that, the rational numbers. How we can define the rational numbers. As you see, dear students, the rational numbers, let's all R is called a rational number if R can be expressed as P by Q, where P and Q are integers. So there are three conditions has to be satisfied for a number to be a rational number. The first one is that, first is that a number R which is expressed in the form of P by Q are called rational numbers subject to the condition. The first condition is that P and Q are integers. It could be negative also, no problem. Second one is that Q should not be equal to 0. And third one is that HCF of P and Q is equal to 1. Correct? That is the highest common factor of P and Q. For example, if you take the number 3 by 2, 3 by 2 is a rational number and it is expressed as P by Q, where P is equal to 3 and Q is equal to 2. Obviously, Q is not equal to 0, which is 2, and HCF of P and Q is equal to 1. So that is why we can say that 3 by 2 qualified to be a rational number. Now, 0 is also a rational number. How you know, dear students, that we can express 0 as 0 by Q, where Q is not equal to 0, Q is an integer, and highest common factor between 0 and Q is 1. Now, the interesting part is that, let's consider a rational number 3 by 2, and let's find its decimal expansion. Its decimal expansion is what? 1.5. Correct or not? Now let's take another rational number, okay, and the number is 2 by 3. Correct. Now the decimal expansion of 2 by 3 is, what, dear students? It is 0.666 and it continues. So what we see is that the decimal expansion of a rational number either terminating, or if it is non-terminating, it is recurring. That means repeating. In the first case, what we see, the decimal expansion of a rational number, which is 3 by 2, is terminating. It terminates at the first decimal point, 1.5. But if you look into the second one, 2 by 3, that is 0.666 and so on, we see the decimal expansion of 2 by 3 is non-terminating but repeating or recurring. All these terms are synonyms in this context. We see here that 6 is actually getting recurring, 6 is repeating. Correct. So we will put more thought on that how the decimal expansion of a rational number we can detect whether it is terminating or non-terminating. Okay, I hope things are clear so far. Now let us take another example. Okay, if we take a decimal expansion of a number called 19 by 14, let's take a number called 19 by 14 and let's see its decimal expansion. Okay, then So if we see the decimal expansion of 19 by 24, 19 by 14, sorry, 19 by 14, as you see in the screen, is mentioned as 1.3571428571428571428571428 and so on. What we see, it is non-terminating but recurring. Why it is recurring? Recurring in the sense that we see that the number 714285 is recurring forever. That means non-terminating. So you see here 714285, that is 714285. This is repeating here, then it is repeating here, then it is repeating here. If you see that 714285. So as it is non-terminating, means repeating forever, the symbolic way of present this number is 1.3571428 with a bar. That bar, as you see, that means what I'm saying is that 1.3571428, as you see, 714285, it is actually recurring. And as it is recurring, and that's why the symbolic representation is that to give a bar on that the numbers which are actually repeating or non-terminating or recurring. All these words are synonym in context of the discussion. So our next point, what we are going to discuss is that how to find multiple rational numbers in between two given rational numbers. So before that, I wish you to have a look into whatever we have discussed so far. Just a quick look into it, that about the rational numbers and how to what is its decimal expansion. Just have a quick look into it. Okay, that the entire rational numbers and its decimal expansion, that it terminates, and if it is non-terminating, it is recurring. Okay. Okay, dear students, now let's find a very interesting discussion, is that how to find multiple rational numbers between two given rational numbers. Okay, and here it is. So let's take, there are two rational numbers, A and B. Okay, A and B are two rational numbers. Let A and B be given two rational numbers where B is greater than A. Means without loss of any generality, we are assuming that B is greater than A. Suppose we need to find n rational numbers between A and B, and to get all these n rational numbers, we need to follow the steps as mentioned. Step 1 is that we need to find a value D, which is B minus A by n plus 1. That is the step 1. Okay. So for example, let's take an example that we have two numbers. The first number is 2 and second number is 5. In between 2 and 5, we need to find 4 rational numbers. So if we map this problem statement with the theory we are discussing. So we can say that A is equal to 2, correct or not? B is equal to 5 and N is equal to 4, correct? So then if this is the case, so between 2 and 5 we need to insert 4 rational numbers. So first we need to find the step 1 is that we need to find a number D, and that number D is equal to B minus A by N plus 1. B minus A by N plus 1. What is B? B is 5. 5 and A is 2. 5 minus 2 is 3. And N plus 1 is 5. 3 by 5. So we get the value of D is equal to 3 by 5. Now in the second step, we can find that N rational numbers between A and B as obtained as A plus D, A plus 2D, A plus 3D, and so on up to A plus ND. So what we get in step 2? In step 2, what we are going to get is the first rational number in between 2 and 5. We can find is that A plus D, 2 plus 3 by 5. Correct? 2 plus 3 by 5. Then 2 plus 2 into 3 by 5. That is the second rational number. Then 2 plus 3 into 3 by 5. Correct? And the last one is that 2 plus 2 into 4 by 5. I'm sorry. The last one should be 2 into 2 plus 4 into 3 by 5. Correct? So these are the 4 rational numbers. So that means 2 plus 3 by 5, 2 plus 6 by 5, 2 plus 9 by 5, and 2 plus 12 by 5. Correct? So these are the steps to be followed to find that, in rational numbers between 2 rational numbers A and B. I hope things are clear, dear students, and we can proceed to the next one. So the next point, is very important. Determining the nature of the decimal expansion of rational numbers. Determining the nature of the decimal expansion of rational numbers. We know, as we just discussed briefly, a number which is a rational number, its decimal expansion either terminates, or if it is not terminating, it must be repeating, means its numbers after some decimal places must be repeating. Now the question is just by looking into a rational number. That means what is a rational number? A number which can be expressed in the form of P by Q, where P and Q are integer, Q is not equal to 0, and HCF of P and Q is equal to 1. Okay. Now, just by looking into a rational number, can we say whether its decimal expansion is terminating, or if it is not terminating, can it be recurring? And if it is recurring also, can we say after what decimal place, till what decimal place the number is actually recurring? We want to discuss on these points. So, let me keep the note first, and then we will start our discussion. So, as you know, dear students, we know a number is said to be a rational number if it can be expressed. Sorry, there is a small mistake here. If it be expressed, okay, in the form of P by Q, where P and Q are co-prime, when HCF between two numbers is 1, then we can say these two numbers are co-prime to each other and q is not equal to 0. For example, as we have just seen, 5 by 4. 5 by 4 is a rational number. Okay, now if we see that 10 by 8, if 10 by is a rational number, as long as the definition is concerned, 10 by 8 is not a rational number because the HCF of 10 and 8 is not 1. Correct? It is actually 2. But we can always represent the number 10 by 8 into the reduced form as 5 by 4. And that 5 by 4 is definitely a rational number. Because 5 by 4 is expressed in the form of p by q, where p is 5 and q is 4. Second one is q is not equal to 0, that is 4 is not equal to 0. And third one is that HCF of 5 and 4 is 1. Correct, my dear students? So what we understood is that this is the way we also discussed earlier. This is the way we can represent a rational number. Now the decimal expansion of a rational number must hold any of the following two properties. Means when you make a division of p by q, you get a decimal number. No? Now the decimal number hold any of the following two properties. The decimal number hold any of the following decimal expansion of a rational number hold any of the two properties. First one is that its decimal expansion terminates, or its decimal expansion is non-terminating but repeating or recurring. Repeating, recurring, all these are synonyms. So we are going to discuss that how we can find that one, okay, just by looking into the rational number. Now, just by looking into a rational number, let me keep the notes first. Now, dear students, this is an important part of discussion. Now, by looking a rational number x, which is expressed in the form of p by q, where p and q are co-prime and q is not equal to 0, how can we tell whether the decimal expansion terminates or its decimal expansion is non-terminating but repeating? Following is the answer. So, from the number that is p by q, we concentrate on the denominator. Let me use a different color. Let's concentrate on the denominator, q. Now, if we can represent q in the form of 2 power m into 5 power n, if we can represent q in terms of 2 power m into 5 power n, we can conclude, yes, the decimal expansion of this number p by q terminates. Not only that, we can tell, it terminates after k places of decimal, where k is the larger of m and n. Correct, no, dear students? Let's take an example, okay? Then it will be very clear to us if we take an example. Things become simple, when we take an example. So let's take a number that, let's take a number called, 3 by 80. Okay, let's take a number called 3 by 80. Now, 3 by 80, if we need to decide that whether the number decimal expansion of 3 by 80 terminates or not, we just need to focus on the number 80. We just need to focus on the number 80, and we need to see whether 80 can be expressed in the form of 2 to the power m into 5 to the power n or not. So what we see, dear students, so 80 is equal to 2 to the power 4 into 5 to the power 1. Correct or not? So as we are able to express 80 in terms of 2 to the power m into 5 to the power n, that is here m is equal to 4 and n is equal to 1, we can say yes, it is terminates. Its decimal expansion terminates. And not only terminates, we can tell at what decimal point it will terminate. So it actually terminates after the 4 decimal places. Okay, without making a long division, we can say this thing. Now, dear students, if you make a long division of 3 by 80, what you are going to get? You are going to get 0.0375. If you make a long division of 3 by 80, what you are going to get? You are going to get 0.0375. 0.375. You see, after 4 decimal places, it actually terminates. 0.375. These are the 4 numbers after the decimal places. Clear, I hope. So what we understood is that the first point is that if q is expressed in the form of 2 to the power m into 5 to the power n, where m, n are non-negative integers, that is, if x can be expressed as p by 2 to the power m into 5 to the power n, where m, n are non-negative integers, we can say decimal representation of x terminates. Moreover, we can say it terminates after k places of decimal, where k is the larger of m and n. Correct, not dear students? Now the second part is that if q cannot be expressed in the form of 2 to the power m into 5 to the power n, where m and n both are non-negative integers, that is, x cannot be represented as p by 2 to the power m into 5 to the power n, where m and n are non-negative integers, we can say decimal representation of x is non-terminating but recurring or repeating. Let's take an example. That will be, things will be clear. So now if you take a number called 3 by 19. Now, dear students, that 19, the 19 you cannot express in terms of 2 to the power m into 5 to the power n, isn't it? So if you take the number 19, you will not find any value m and n so that you can express 19 as 2 to the power m into 5 to the power n. Hence, you can say, yes, its decimal expansion is non-terminating, but it is recurring. You got my point, dear students? And if you make a long division, you will find that it is actually repeating. Okay. So this is the point what I wanted to discuss about the decimal, expansion of a rational number. Now, apart from rational number, there is another number is called an irrational number. What are irrational numbers? That we'll also discuss, touch base today, and then we will discuss its decimal expansion as well. As a side note, remember, unlike a rational number, the decimal expansion of an irrational number never repeats or terminates. That means what? If you find an irrational number like square root of 2, square root of 3, square root of 5, its decimal expansion neither terminating nor repeating. Okay. Take a very powerful calculator, find the value of root 2. You will find that it's numbered after the decimal point. You will not find a pattern to conclude that whether it is repeats, and at the same time it is not terminating. Same thing for root 3, same thing for root 5. When you define that, why it is called irrational, that word irrational actually very meaningful in context to the discussion. So for example, that a rational number is that number which we generally use in our day-to-day life. Okay. For example, you go to a shopkeeper and ask for, hey, I want, 3/2 kilogram of potato. Okay. The moment you say, I need 3/2 kilogram of potato, that makes sense. Okay. That shopkeeper will understand. Okay. Uh, I need to give 1.5 kilogram of potato. Perfect. Okay. Because it terminates. That's why it is perfect. Now, if you go to a shopkeeper and ask that, okay, I need to, you please give me 2/3 kilogram of potato, that also makes sense little bit, because 2/3 is equal to 0.66666 is continuous. That means on approximation, you can say it is 0.67 kilogram of potato. And that also makes sense. But if you go to the shopkeeper and ask, give me √2 kilogram of potato or √3 kilogram of potato, that is confusing. The shopkeeper may not heard about all these things. So irrational things is something which we do not use in practical. But here I am going to tell you, there are few common number systems, not number system, the few common, constant, okay, which is very useful, and we use those numbers as a rational number. But if you see very, fundamental definition of point of view, those constant are actually, irrational number. One such is called the pi. If you recall, dear students, so what is pi? The pi, what we defined, let me use a different color. If you recall, the pi is the number which is a mathematical constant, is the ratio of a circle's circumference to its diameter. Correct? So pi is what? Is a mathematical constant, and it's defined as its representation like this, what I wrote, the Greek symbol pi. And its definition is that it is a ratio of a circle's circumference, okay, to the, and its value is mentioned. If you see the value, its value is never terminates, okay, and that and doesn't repeat as well. How it actually being formed? Let me give you a little background about that, how the number pi is formed. Suppose you take a circle, use a different color. Suppose you construct a circle. Now, suppose this is circle C1, and you find the circumference of the circle C1. So let's define that circumference by P1. And you find the diameter of this circle, that is D1. And you compute the value P1 by D1. Now you construct another circle. That circle should be little smaller than the previous one. And let's give the name of the circle as C2. And similarly, we find its entire circumference, that is P2, divided by its diameter D2. Correct? No? So this is the diameter D2. And now let's construct a very big circle. Maybe a circle like this. And let's give the name of the circle as C3. And here also we find the circumference of the circle as P3 and diameter of this circle as D3. Correct, no, dear students? So this is D3. So what we will observe, dear students, we will observe that P1 by D1 is equal to P2 by D2 is equal to P3 by D3. Always. Okay? Always, in the sense, what I say is that the value will never always find very accurate. But you will find all these values, P1 by D1, P2 by D2, P3 by D3, you'll all find they are very close to each other. But if you actually find the value, you'll find that its decimal expansion is non-terminating and non-recurring. Now, if some numbers decimal expansion is non-terminating and non-recurring, what we define? we define this number as an irrational number, and that actually happens. But you know, dear students, as I give an example, that irrational number are not very practical. So pi being an irrational number is not very practical to use in mathematics, but pi is used a lot in mensuration, in trigonometry, a lot. You will see as time goes by in the next few years that pi is used a lot. So then that approximate value of pi has been obtained as 22 by 7. So what we see is that the approximate value of pi, if we consider as 22 by 7, now 22 by 7 is a rational number, and it is very practical, very easy to use this number 22 by 7 rather than an irrational number. But what is that irrational number? I would like to show you. So I would like to read this statement, and please listen to it. And as you see, the note is in front of you. Here is to be noted that pi, the number which is a mathematical constant, the ratio of a circle's circumference to its diameter, is an irrational number, and its value is mentioned as 3.141592653589238462643383327, and so on. And if you look into this pattern, dear students, you will find there is no pattern, there is no recurring digits, and there is no it is not repeating, which is non-terminating and non-recurring. So particular number sequence is representing after, as no particular number sequence is repeating after a certain period. We generally consider the approximate value of pi as 22 by 7, which is a rational number with decimal expansion is 3.142857. Okay, if you divide actually 22 by 7, what you will get? 3.142857, 142.857, 142.857, and so on. That means 142.857 is actually a repeating, that is recurring. And that's why for a symbolic representation, we give a bar on that number, that is 142.857, to represent it. Correct or not? But in a pure mathematical notation, pi is an irrational number, hence cannot be equal to 22 by 7. But we approximated the value of pi as 22 by 7 as it is used extensively in different mathematical formulas and mathematical concepts, and we'll see all these things in the near future. So with all this, dear students, I would like to conclude the class for today. In the next class, we will discuss in details about irrational numbers and how we can represent rational number and irrational number in the number line and relevant problems. Till that happen, so I will strongly recommend, so please go to www.KonarClasses.com and appear for DPP, that is daily practice problem, and PT, that is called practice test. Okay, and all of you have accounts to this online test platform, and you know how to use it. I just repeat this statement. Thank you very much, and we'll meet again in the next class.